video is the first in a 4-part series showing how we fit data on our WITEC Raman. We are using neon lines to correct for instrument drift throughout the day and also to correct back to what our instrument was like when we ran our gas cell calibration. But you can tweak this for different instruments, and there are some other examples showing exactly how to do this. So as normal, you are going to want to pip install diode fit if you haven't done so already. And the way that I have structured this data is you are basically going to make sure that, one second. So we are working in this example, so you can download this entire example off GitHub if you want to. So this is example 1B. The spectra from the WITEC is in one folder and the metadata is in another. Okay. So you're going to import all of your Python things, and then this is where you're going to tell Python various things that you've done. So I have asked you to tell me what folder your metadata is in. So here we are saying that we have put this notebook in sort of the overall folder. That's the day folder, so that's the entire day of Raman analyses. And then there's a subfolder with my metadata and a subfolder with my spectra. The file type is important to put. So these are headless text files. So that basically means there's a column of data for the wave number and a column for the intensity, but there are no headings. Various other file types, look at the documentation. And this is a TXT file. Now the other thing we have to say is these files, if you look in here, you'll see we've added a prefix. So that 05, 06, 07, that's just an output option on the WITEC. So here we're saying the prefix is true, and the string, so the characters which are separating the prefix from the rest of the file name, is a space. Final thing, if you have a WITEC instrument, you're going to say whether or not your instrument has true power built in. This basically gets the power that you use for your analyses. And these settings are going to be used throughout these 4 steps, okay? So we're setting them all here, even though we're not using them all in this exact notebook. So we're saving these in this pf save settings function. And what this basically does is it makes a little settings file in here. Hold on, let's just go down a level, sorry. It makes the settings file where it has stored, pull this over, has stored all of those settings. So you don't have to type them again in every single notebook. Okay. So the first thing we're going to do is we're going to get all of the files which are acquisitions of neon. So the way you're doing this is you're telling it where your spectra is stored, and you are basically saying what string is in all of your neon files. So in this case, we've used the letters NE. You might have used M capital E, you might have written out neon. Whatever you've done, it's just going to be looking for files which match that string. We can exclude a string, so say there was some overlap with the diode ones, we are just going to put, we're excluding any of the files which have the word diode in. That might be Kilauea, that might be whatever you've decided to call them. Okay, the other thing you need to tell it is the wavelength of your laser. And then what this function does is it calculates the ideal neon line position. So the neon spectra is an emission spectra, and how that appears on your Raman in terms of the wave number is a function of the wavelength of the laser. So we're going to run that. So we see for this wavelength, this is what we use at Berkeley. The neon line emission in air has this value, and the Raman shift is over here. You're then going to pick 2 lines. This is conventionally how this is done. There are various criticisms of this that we discuss in the diode fit paper. We find it works pretty well as long as you always choose the same lines for calibration and running. So we're going to use the 1117 and the 1447 line. What we're basically saying is give us the ideal splitting for those lines, so the ideal distance between those 2 neon lines. You don't have to type the exact line number, it's basically going to find the closest line number to the number you put in. So you can see the ideal value of this line is 1117.08, 1447.56, and a corresponding splitting of 330. You're then going to select a single neon file, okay, and this allows you to tweak the peak fit. So here we are just taking the first file. Now, what this function does is it basically allows you to look at your spectra, and more importantly, it is using SciPy to try and find the prominent peaks in your spectra. So the SciPy find peaks function has these parameters: height, distance, prominence, width, and threshold. The most important ones to tweak are basically the prominence and the height. So what you want to do is you want to run this and you want to check that it has found the peaks in the region you're interested in. So I said I was interested in about 1117 and 1447, and you can see it has got these peaks. This is what you're going to have to adjust for different instruments. You might have way more intensity. Here we're looking at about 4,000 counts. So if I put my prominence up to 500, you can see it does actually still get up. So you can basically tweak this around. This is SciPy, and you basically want to make sure that it is putting yellow stars on these peaks. Okay, so once you've got that and you tweak those parameters, the other things you're going to have to tweak is the actual peak fitting parameters itself. So what do we decide when we're fitting peaks? Well, firstly, we have to select background positions, and we have to fit a baseline between those backgrounds. So you can see here we are selecting the polynomial fit that we want to do for peak 1, which is the left-hand peak here. So we're saying we want to do a linear baseline basically, and the same for peak 2. We are expressing the background positions relative to the position of the peak. Okay, so this means that we want our background 50 units to the left and 25 units to the left of the first peak. So these default values are stored in this neon peak config function. And you can change any of these parameters at any time by just typing the parameter name, peak 1, and then you could say 5 instead of the default being none. And you could list any numbers of these. So you could change the model name to be a Voigt model rather than a pseudo Voigt model. So that is how you edit the default parameters. And you can see down here, we are basically printing it to have a look. And then we are tweaking this for our instrument. So really key parameters are the background positions and the sigma of the peak, so how broad the different peaks are. Okay. So then you can basically fit one neon line and see if those parameters look okay. So let's have a look down. So you'll see for the 1116, 1117 peak, there's actually a subsidiary peak on its flank. And this means we have to fit 2 peaks, otherwise we're not going to get the right value. So you can see up here, you set that with peaks 1, so peaks for the left-hand one, we're going to set that to 2. And then for the 1447, 1448 peak, we can fit it with a single peak. So we're happy with that. This graph shows the residual of the fit, so basically how well this best fit is fitting the data. You might think that a residual of about 600 is quite a lot. You'll see it's actually quite offset from the peak positions. The peak position is shown by the black line, so you can see the residual is really, really small on the peak. It's basically these points it's struggling with a bit. And this is a residual of 600 out of 10,000, so it's really not so bad. The other important thing is the background position. So you can see here we have selected 2 background positions, and you can see most importantly up here, this is the offset from the peak positions. This is the background between -40 and -25. You might wonder why we've done that. We don't want to define the absolute peak positions for the backgrounds because every instrument this will be different, because that x-axis is a function of the wavelength of the laser. So this is a way that you can run this on different instruments. You're not going to have to change it as much as if we'd express them in terms of wave number. So here we've chosen 2 background positions, and here we have chosen 3 background positions. So you can see that up here. So upper background, so peak 2, we're looking at the backgrounds here. We have the lower background, that's between -40 and -30 to the left. We have the upper background for peak 2, and the first one is between 10 and 15, and the second one is between 25 and 40. So you can see 10 and 15, 25 and 40. And you could set 2 different upper background positions for peak 1 as well. Here we've just set them the same. Okay, so that we are happy with that. And the point of diafit is you tweak the fits for one of these. Once you tweak them for one of these, you're good to go. So now we loop through all of the neon lines and you're not having to retweak them. And most importantly, once you've tweaked this once for one instrument, you don't have to tweak it again, realistically. As long as you inspect that it looks reasonable at any one time. So what we're doing here is we're just updating. We guessed a sigma value, so we guessed 0.6 and 0.3 for the width of the peak, which we update it with what we got for that first one, because that's better than my random guess. Now this loop neon lines file, this basically loops through every single neon line and fits it. So you can see we've given you a little progress bar, so here we're fitting 10 neon lines. So we're just going to let that go. And you can see here it's plotting the figure afterwards. So you're going to be able to look at the peaks. If you have like 70 neon lines, you might want to plot a few of them. If you turn that off, the code will run a lot faster. So I'm just going to flick through, and I am looking at these, I'm looking at the residuals, I'm looking at the background positions, and I am happy with these fits. Okay. So I've already fitted the peaks. So this is also meant to take a really long talk. To make a correction model of how my instrument is drifting with time through a day, I not only need the measured distance between the neon peaks, I also need the time at which that was done. So the WITEC metadata files contain timestamps, so we're going to extract that. So the first thing we're going to do is we're going to identify all of the metadata files. So we're looking in that folder, meta path, we find above, and we're looking for any file which has, a string containing neon, like above. There's then this function for WITEC, stitch metadata in a loop, and this basically extracts all of the useful metadata. So you can see you've got the file name, you've got the date, you've got the laser power, you've got the integration time, the accumulations, the magnification you use. And most importantly, we've added this column here. This is the seconds since midnight. It's basically how far through your day after midnight you acquired this neon line. And this is the x parameter we're going to use to build that regression model. So what you might have to do is you might have to just, get those file names. So we are basically now, we have a data frame, which is our metadata, and we also have a data frame, which is our peak fits. So we can just go up here and have a look. So this data frame is called df2. Okay. So let's just have a look at these so you understand the next step. Okay, so this has a file name, and it has all of this peak fit information for the neons we want. We also want to merge it with this data frame. So we just want to make sure the file names are the same, and this is when having a prefix can mess you up. So we're just going to check that the file names for the metadata look right, and that the file names for the spectra, and you want to check these look the same. If they don't, you're not going to be able to automatically merge them. And then we're just making a new column called name for matching on the metadata data frame and the data frame for the spectra fits. We then combine them together, and we have a combined data frame which has our peak parameters and it has our timestamp, importantly. Okay, so now we're just going to sort them by the time after midnight. And then we're going to use this function which takes the data frame you've combined and it basically plots some peak parameters. So what it plots to start with is the position of peak 1. So that is that 116, 117 peak, and it's plotting it against time. So you can see this peak position is drifting through time. This matches temperature in our lab really, really well. This is a known problem, and this is why we're doing this correction. I'm also plotting things like the peak 2 center against the neon correction factor, just so you could see. The most important plot by far is this one, the neon correction factor versus the seconds against midnight. This shows how our instrument is drifting through the day. Now you might have some outliers. Sometimes you get a funny peak fit, sometimes, maybe you forgot to turn your laser off when you're acquiring neon and you have something on top and it just looks garbage. So this function here, filter neon line neighbors, you can basically define an offset. So this offset here, 0.001, if we make this really small, you can see it has removed these neon lines, which are more than that distance from their neighbors. So as we make this smaller again, you can see we keep them. So you basically want to adjust this number until you get rid of the ones which look really rubbish. Okay, the final step is to filter out any with a really large error. So you might have some which are kind of on the trend, but you're not happy with them because they have a gigantic error bar. So you could just say, the error bar, so the y-axis coordinate that you're not happy with, and then it will filter those out. And then finally what we do is we fit a polynomial. So you can see this is now our correction model against time. So say we acquired our dyad at 53,000, you would read up and this would give you your neon correction factor and critically the error for that as well. So now we've saved this, after we fit our spectra, we can just simply load in this model and apply it. So this saves a lot of time manually fitting neon. So see step 2 for the next steps.